Well, in the meantime that people are starting to connect, I just wanted to say a few words to introduce these new series of talks that we are organizing here at Space Telescope in collaboration with the Johns Hopkins University. And first of all, I want to thank you, all of you, for being with us here today. I am Matilde Mingozzi. I am a Space Telescope postdoc working with Bethan James and Alessandra Loisi. And today I will share the talks with John Debs. And so the idea of these talks, of this series of talks for these discovery seminars is that early career researchers, as you all know, were particularly affected by the pandemic in the previous 2 years, with reduced travel and networking opportunities that have been heavily impacted and have impacted our ability to advertise our science and to build professional networks, and so to develop our careers, of course. So this is the aim of the Discovery Seminar Series, to advertise the work of the postdocs here at Space Telescope and Johns Hopkins to an international audience of astronomers. And from now to July, we will have these seminars every 2 weeks, or there are several dates that you can see on the website. And the people that are organizing this, I want to thank all of them. Apart from me, it's Alessandra Loisi, Ramona Augustin, John Debs, Andrew Fox, and Mireia Montes, with the help of the event planning group of Space Telescope. So I think that we can start. There are enough people on. So I want to introduce you the first speaker of today, that is Cassi Lochhaas. Cassi got her PhD from the Ohio State University in 2019, and then she came to Space Telescope as a postdoc during that year. She's primarily a theorist interested in galaxy evolution, the circumgalactic medium, and galactic winds. And today she will talk about the structure of the circumgalactic medium in high-resolution cosmological simulations. So Cassi, if you want, you can share your screen, and we can start. I can't hear you. Probably you are muted. But I can see your screen.
Can you hear me now?
I can hear you now, yeah.
Okay, great. Sorry about that.
No worries.
Let me share my screen. Okay, I just wanted to say thank you very much to the organizers of this talk series for putting this together, and thank you for everyone for coming today. So I am going to talk about some of the work that I've been doing over the past couple of years at Space Telescope, looking at the structure of the circumgalactic medium in high-resolution cosmological simulations, much like the simulation that we are watching this video of here. This is showing us, this is actually one of the FOGGIE simulations, which I'll talk about in just a minute, where we're watching a galaxy slowly form from lots of other galaxies merging together and sort of building up its structure over time. So sort of in very broad strokes, the circumgalactic medium is the region just outside of galaxy disks, but still we think within the virial radius of a galaxy's dark matter halo. And it is really this region of space that is the conduit between galaxies and the rest of the universe, because any galaxy fuel, any material that falls onto the galaxy to fuel star formation and cause the galaxy to grow over time has to first pass through the CGM on its way there. And then any outflows that come back out of the galaxy as launched by star formation feedback or AGN also pass into the CGM. And clearly we can tell from videos like this one that it's a very highly structured and dynamic environment. So what I'm most interested in is understanding how that structure and those dynamics within the CGM impact galaxy evolution as a whole, and what models we can actually use to describe this rather complicated system. So one of the sort of very basic zeroth order models that we have for the CGM is shown by this cartoon here, where we see a galaxy at the center, a nice disk galaxy. Perhaps it's accreting gas through these inflow filaments that are here colored blue. If there's a star formation or an AGN in this galaxy, it's launching outflows back out into the CGM. And if it's a massive disk galaxy, those outflows will be roughly biconical, coming out above and below the disk. Perhaps some of those outflows are recycling and falling back onto the galaxy. And then sort of in between the accreting filaments and the outflows and the recycling gas is just this diffuse volume filling medium that's here shown as purple. So this cartoon works fairly well as sort of just a very basic understanding of all of the different processes that could be happening in the CGM, but there's still a lot that we're trying to understand. So in particular, what I've been focusing on and that I'll talk about mostly in this talk is sort of how galaxies accrete gas from the CGM. We really don't understand exactly the processes that lead to that. And in particular, what keeps all of that gas out there from just sort of gravitationally free falling onto the central galaxy. So for a long time, one of the most common assumptions that has been used for describing the overall model of the CGM is this idea of a hot hydrostatic halo. So what this model says is that the CGM is filled with static hot gas at the virial temperature, where the gravitational potential of the galaxy and its dark matter halo is opposed by the gas pressure, the thermal gas pressure of that gas. So if we have a massive galaxy, like roughly Milky Way-like galaxy, there's rather a lot of gravitational pull from that galaxy and its dark matter halo. So that means we need rather a lot of thermal gas pressure to oppose it, and therefore a high temperature. So this is where the idea of a hot hydrostatic halo comes from. So this model is based on an idea that astronomers everywhere love, and this is the idea of equilibrium. We see equilibrium in all different aspects of astronomy. This exact same hydrostatic equilibrium is used in stellar structure models. We also have pressure equilibrium between phases of gas in the interstellar medium. It really shows up everywhere. So models like this one that assume that the CGM is in equilibrium are actually built on an even deeper assumption of equilibrium within galaxy evolution as a whole. So one of the most common ways of thinking about galaxy evolution is thinking about a balance between gas flows into and out of the galaxy. One way to think about this is that the inflow rate of material onto the galaxy disk is balanced by that gas turning into stars, and also balanced by any outflows that come back out of the galaxy as launched by star formation feedback or AGN, or just processes occurring within the galaxy. So this sort of apparent equilibrium between these different gas flows actually works really well to describe a lot of the observed galaxy scaling relations that we have. Things like the mass-metallicity relation that gives us the metallicity of a galaxy as a function of its mass, or the star-forming main sequence that gives us the star formation rate of a galaxy, again, as a function of its mass. So if we have this equilibrium in our galaxy evolution models, we might expect there to be equilibrium in the CGM as well. But there's a lot of observational evidence that the CGM is not just this static ball of hot gas in equilibrium like we would expect from the hot hydrostatic halo model. In particular, we can observe there's a lot of cool gas there as well. We see absorbers at around 10 to the 4 Kelvin, but we would expect that hot hydrostatic halo for a Milky Way-like galaxy to be at around 10 to the 6 Kelvin. And in addition, those absorbers show significant velocity shifts relative to the velocity of the central galaxy, and also significant velocity widths that indicate there's sort of a lot of gas dynamics and sort of kinematic motion that's occurring in the CGM. And we saw that in the video I showed right at the beginning. All you really have to do is watch one of these movies from one of these simulations, and you can see that there is a lot of structure and a lot of dynamics occurring in the CGM. So what I've been interested in trying to understand is how does this sort of potential non-equilibrium in the CGM fit into equilibrium galaxy evolution models. So in particular, there are two different equilibrium models for the CGM that I want to talk about today. This is hydrostatic equilibrium, the idea of the hot hydrostatic halo that I just introduced, and then also at the end I'll briefly touch on virial equilibrium and the associated virial temperature. So what I do is I use high-resolution cosmological simulations to test whether these equilibrium assumptions hold up in the simulated circumgalactic medium. The simulations that I use are called FOGGIE. This stands for Figuring Out Gas and Galaxies in Enzo. One of these simulations was the same one that I showed at the very beginning. I'm showing it again here with density, temperature, and metallicity projections. So FOGGIE is a handful of cosmological zoom-in simulations where we have a significant amount of cosmological structure, but then we pick a handful of Milky Way-like galaxies to zoom in on and place extra resolution within the simulation within and surrounding those galaxies. The special thing about FOGGIE that other cosmological simulations don't do is we have a box that's about 200 co-moving kiloparsecs on a side that we place on these Milky Way-like galaxies, and everywhere within that box, the resolution of the simulation is very high. So this means that we can actually resolve the circumgalactic medium out to tens to 100 kiloparsecs, pretty far away from the galaxy, to a very high degree of refinement that allows us to pick out a lot of the structure that we see in the CGM that other cosmological simulations are not quite as good at picking out. So this means that FOGGIE is a very good method for testing these equilibrium models within the CGM. So I'll start first with this hydrostatic equilibrium. And just to remind us all, if you think back to your introductory astronomy courses, the hydrostatic equilibrium equation is actually a force balance equation. What it says is that the radial gradient of the gas pressure is balanced by gravity. So this means that if our gas pressure is declining as we move away from the galaxy, then the gradient is negative, and that balances against the inward gravitational pull of that galaxy. So if these things are exactly equal, we have hydrostatic equilibrium. We can look at what that actually looks like in one of our FOGGIE galaxies. And this is all very preliminary work that I'm currently working on as the PI of an HST theory grant. So what we're looking at here is the thermal pressure of one of our FOGGIE galaxies. Again, this is a Milky Way-like, roughly, galaxy. And what we're looking at here is right at redshift 0. I put a little box around the edge-on galaxy disk just to sort of orient ourselves here. And right away what we can see is that, on average, the thermal pressure does decline as we move further away from the galaxy. And this is what we would expect from a hydrostatic equilibrium model. But again, that hydrostatic equilibrium equation is not a pressure balance equation, it's a force balance equation. So we can actually just convert the pressure that we're looking at here into a force by taking its gradient everywhere within our high resolution simulation. So that's what this looks like here on the right. This is the gradient of the pressure, which means it's the force exerted by the thermal gas pressure. So in this plot, anything that is a sort of a bluish green color is indicating an outward force, and anything that's a brown color is indicating an inward force. So this means that we don't have just the perfect hydrostatic equilibrium that we were expecting, because in that case, this whole slice would be sort of this bluish green outward force that slowly turns into white as we move away from the galaxy. But clearly we don't see that. There's a lot of small scale structure here. We have both inward and outward forces, both being exerted by this thermal gas pressure that vary significantly across small scales of just a handful of kiloparsecs or so. And we see this especially within this 200 kiloparsec box that we have, where we have the very high resolution within the FOGGIE simulations. There's also some large scale structure as well. In particular, we can see, this galaxy at this snapshot in time has a kind of peculiar one-sided outflow to it that we can see it has actually very strong forces associated with it. And there's also an inflowing filament that I've marked here that doesn't really have any thermal pressure associated with it because it's very cool. So it shows up as white on this plot. But we saw in that video earlier that there's a lot of dynamic motion. There's sort of a lot going on in the CGM, more than just thermal gas pressure. And so when we think back to our force balance equation, we can include a whole lot more forces. We've already talked about the thermal force that comes from the thermal gas pressure. We can also have a turbulent force that's being exerted by a turbulent pressure, which is also in an outward direction if that pressure is declining as we move away from the galaxy. We can have a ram force that's being exerted by bulk inflows and outflows within the CGM, sort of smacking into any material that's already there. That can be either an inward or an outward force. Rotation exhibits this pseudo force, the centrifugal force that is pretty much just in the outward direction. And then, of course, we have gravity. So we can take a look at, for example, what the turbulent pressure and force looks like. So this is the exact same image that we were looking at before. But now we're looking at the turbulent pressure on the left and the force exerted by that turbulent pressure on the right. So again, I put the little box around the disk just to orient us. And we can tell that this turbulent pressure does still decline as we move away from the galaxy. So it is still providing a supporting outward force, sort of supporting against gravity. But if we look at the right plot here, we see what that force actually looks like. We can tell there's still a large amount of that small scale structure that we saw before. And we can still see that one-sided outflow that has very strong turbulent forces associated with it as well. So in the interest of time, I won't show all of the pressures and the forces for all of these other different types of forces, but if you're interested, feel free to ask at the end. But for now, let's just add up all of these different forces together and look at just what is sort of the net force that is acting on any given parcel of gas within the circumgalactic medium. This is what that looks like, where again, any pixel here that is colored sort of a blue-green is an outward net force, and anything that is brown is an inward net force. So if we had a perfect force balance here, inward and outward forces perfectly balancing against each other, this whole slice would be white, and that's very clearly not what we see. We have these large-scale structures again of this one-sided outflow and this inflow filament. We have the very small-scale structure within our high-resolution box. And altogether, what this means is that any given parcel of gas within the CGM is actually not in a perfect force balance. On these very small scales, we have this huge variation between inward and outward forces, and also with the strength of those forces. So if we think about sort of one of the standard ways that the CGM is observed by taking a spectrum of a background quasar, looking for absorption in that quasar spectrum, that's probing just a very small scale within the CGM where these forces are not in balance. So that means if we're trying to understand our observations of the CGM from starting with a global model like this hydrostatic hot halo, we cannot specify the structure that is actually there on the smallest scales. So you might be able to convince yourself that despite all of this small scale structure, if you were to sort of blur your eyes and squint, perhaps when you average out over very large scales, you could average these colors together into that white that we're looking for that force balance. Let's quantify that and take a look at what that actually looks like. So I hope I've convinced you there's a lot more to the CGM than just the thermal gas pressure, but we can quantify how much the thermal pressure is holding up the gas against gravity compared to the other forces that are acting in the CGM. And the way that I'm going to do that is show the ratio of each of these forces to the force of gravity. And we're looking at this as a function of radius moving away from the galaxy, where the central galaxy is at 0. And I've put as the vertical dashed line here the virial radius of this galaxy's dark matter halo. So on this plot, if this ratio of any of these forces to the force of gravity is 1, that means that it is exactly balancing against gravity, and that force is sort of holding up that gas, keeping it from just gravitationally falling onto the CGM. If this ratio is 0, then that means it's really not contributing to supporting the gas against gravity at all. So if we look at that thermal pressure first, that the force exerted by that thermal pressure is this red line, right away we can tell that it's just not enough to hold up all of that gas in the CGM against gravity, because this ratio, this red line, is below that ratio of 1. But if we start including some of these other forces, like turbulence, for example, as this green dashed line, this helps a lot, very close to the galaxy, not so much in the outer parts of the CGM. But let's now put in rotation as this blue dot dash line. This helps quite a bit, especially in the inner parts of the CGM. And now we can actually add all of these together and again look at our net force acting on all of the gas in the CGM as this black line. And what we can see is that in the outer part of the CGM, this black line is very close to or oscillating about this ratio of 1, meaning that all of these forces are working together to oppose the gravitational pull and keep all of that gas from just collapsing inward onto the central galaxy. However, you'll notice in the inner CGM, we actually have a ratio greater than 1, meaning that there is more sort of outward force than there is gravity pulling it back inward. So this is actually indicative of the fact that there's a pretty strong outflow very close to the galaxy that is causing all of those outward directed forces in that inner part of the CGM. So our conclusion for hydrostatic equilibrium is that there is no such thing in the circumgalactic medium. It's neither hydrostatic in that we need more than just that thermal gas pressure, nor is it really in equilibrium, as we have a lot of that very small scale structure, such that no given tiny parcel of gas is in perfect equilibrium, and neither is the sort of very inner parts of the CGM, even when you average over all of those small scale structures. So now, in the last few minutes, I want to just talk about the virial equilibrium and the associated virial temperature. But before I do, I want to briefly mention sort of these different regions of the CGM that I hinted at a little bit already. So this is the exact same image that we've been looking at this whole time. Same galaxy, roughly Milky Way mass at redshift 0. Still got that box around the edge-on galaxy disk. But now we're looking at the temperature of the gas surrounding this galaxy. So we can see we have a very cold galaxy disk, but the outflow, that sort of peculiar one-sided outflow, is very hot. And we can also see sort of that inflow filament is pretty cool as well in the bottom right. But it's really this warm or intermediate temperature halo gas, all the green stuff in this plot, that I want to focus on here. Because it's this stuff that's not directly participating in either an outflow or an inflow. It's sort of the volume-filling diffuse medium. And it is this warm halo gas that is generally thought of being at the virial temperature of the halo. So when I say virial temperature here, what I'm talking about is a temperature that depends only on the halo mass and radius. And it comes from some assumptions about the energy balance within the gas of the halo. So what I was interested in a paper that published last year is this gas in our simulated CGM actually at this commonly assumed virial temperature? So let's just take a look at what the temperature of the gas in our simulated CGM actually is. So this is a two-dimensional histogram here, where we're looking at the temperature of the gas near the virial radius, so at a very large distance away from the galaxy, as a function of time as this galaxy evolves. So anywhere on this plot that is a darker color is indicating more of the gas mass is at that temperature at that time. So right away, what we can see is that this temperature is not constant with time. There are these excursions to very high temperatures, even way out near the virial radius, far away from the central galaxy. But it turns out, if I now put the star formation rate as this black line on the bottom here with values on the right axis, we can see that these excursions to high temperatures are actually correlated with bursts in the star formation rate. So it would appear that starbursts within the central galaxy are heating up the CGM briefly, even all the way out at the virial radius. However, at late times when the star formation rate sort of turns into a pretty consistent low level, we do approach a roughly constant temperature, even out near the virial radius in this simulated circumgalactic medium. So the question is this roughly constant temperature well described by the commonly assumed virial temperature? So if I put the virial temperature on here as this orange dashed line, we see that it is not. It turns out that the temperature of the gas in our simulated CGM is actually about a factor of 2 cooler than the usually assumed virial temperature. And the reason why this is because this temperature comes from the virial equation that just relates the potential and the kinetic energies of the gas in the CGM. But in order to turn these energies into a temperature, there's a very common assumption that is used. And that assumption is that the kinetic energy of the gas is purely just thermal energy. It just comes from the motions that are due to the temperature of the gas and nothing else. But we know that there's a lot of other motions that are happening in the CGM. There's rotation, there's turbulence, there are bulk flows, there's a whole lot of dynamic structure that we saw in all of the videos that I've shown. So really, this is not a very good assumption. What if instead we include all of these non-thermal kinetic motions into our term for the kinetic energy in our virial equation up here at the top, and then sort of rederive the temperature? And I'll call this a modified virial temperature. So when I do that, and now this is plotted as the red line on here, what we can see is that this is a much better match to the temperature of the gas that we actually see in our simulated CGM. So clearly this assumption that the only kinetic energy in the CGM is thermal kinetic energy is a very bad assumption. So what this means is that this halo gas is not described by the virial temperature, but rather by this modified virial temperature that just comes from including all of that dynamic motion. And it turns out there's actually some interesting observational implications from having a factor of 2 cooler CGM than we would expect. It could mean that the CGM is observable more at UV wavelengths than at X-ray. It could mean that very cold gas, around 10 to the 4 Kelvin or so, is actually being produced more efficiently, because this 10 to the 5.5 Kelvin is right at the peak of the radiative cooling curve. So there could be even more cool gas that's being produced just by having a slightly cooler CGM. And it could also be the reason why we observe so much oxygen-6 very commonly in the CGM of Milky Way-like galaxies, because it turns out that oxygen-6 ionization fraction peaks right around this 10 to the 5.5 Kelvin or so, much lower temperature than oxygen-7 or 8. So our conclusion for the virial equilibrium is that it turns out the equilibrium equation itself does hold, but we need to include this non-thermal kinetic energy from the turbulence and the bulk flows, which will then drop the temperature by a factor of 2. So I hope I've managed to convince you that we have significant non-equilibrium structure within our CGM on very small scales, and the gas dynamics of the non-thermal motions of the gas in the CGM play a large role in that structure and even in the temperature of the gas. So that means that if we're thinking about our our models for describing the CGM, we really can't start with global top-down equilibrium models like the hot hydrostatic halo. These types of models just can't predict what is happening on the very small scales where we have non-equilibrium conditions dominating, the same small scales that the observations are predominantly probing. So that means that if we think back to our galaxy evolution models where we do have this apparent equilibrium, this means that this equilibrium, as galaxies evolve, must be an emergent phenomenon that comes from averaging over all of this small-scale non-equilibrium structure. So the message that I really want to leave you with here is that when we're thinking about the connection between the CGM and galaxies, don't start from a point of equilibrium. Instead, we want to come to a point where we're starting from understanding all of this bizarre non-equilibrium structure, but then ending up at a point of galaxy evolution equilibrium. And finally, I'll just say I've been, over the course of the pandemic, stuck in my own little theorist bubble, and I'm very interested in collaborating with any observers. If you have a particular system that you're having a hard time modeling, if you want some comparisons to simulations, if the simulations that I showed you today look very interesting, or especially if you're really interested in non-equilibrium weird gas dynamics or something like that, absolutely let me know, and I'm very happy to collaborate. So I'll leave it there and take questions. Thank you.
Thank you very much, Cassi. Thank you very much for the very interesting talk. Very beautiful results. If people have questions, you can raise your hand, or you can post the questions in the chat, and I can read them for you, or you can unmute yourself and ask a question. So please. Andrew Fox has a question. You can ask.
Great, thanks, Cassi, for a really interesting talk. So you mentioned you need these non-thermal motions to explain the virial temperatures and to match the temperatures that are observed. And I was just wondering how much non-thermal motions, like, for example, are they consistent with the line widths that are measured in the CGM? Because there is quite a lot of observational data on non-thermal line widths from absorption lines.
Yeah, that's a fantastic question. So I can't answer the observational comparison part of your question, because that is something I'm very interested in looking into, but I have not done yet. But I can say that when I look at the total energy of thermal versus non-thermal motions, I do find that the energies are roughly equal. So that's actually what leads to the factor of 2 discrepancy in the temperature, just because there's pretty much equal amounts of thermal and non-thermal kinetic energies in the gas. So I'm not sure exactly how that would translate into non-thermal velocity widths, but that's something I'm very interested in looking into.
Great, thank you.
Thank you, Andrew. Let's see if there are other questions from the, I don't see anything in the chat. And we reached the half of the hour, so Tim Ekman has a question. Yes, you can unmute.
Cassie, I'm sure it's probably in your paper, but I'm lazy, so maybe you can. In the plot where you showed the temperature increasing by a factor of 2 or 3 following a starburst, what fraction of the energy supplied by the starburst is required to heat the gas?
Oh, that's a good question. I do not know quantitatively what the answer to that would be. I would guess, though, just because both the thermal and the non-thermal energies actually increase after a starburst. I didn't show this, but I would guess that roughly half of the energy that is being input into the CGM by the starburst would have to go into heating the gas, whereas the other half goes into stirring up more of these non-thermal motions.
Yeah, well, that was the follow-up question. But I mean, it would be interesting to do the numbers because just to show it's energetically feasible, A, and B, maybe this says that you need 100% of the kinetic energy injected by supernovae to do this much work on the CGM, which would be interesting to know.
Yeah, that would be very interesting for sure. We only have thermal feedback in the FOGGIE simulations, so we are a little bit limited in that. But in some ways, that actually makes it a little bit easier to do that calculation. So that's a very good point.
Perfect. Thank you very much, Tim, and thank you very much again, Cassi, for the very beautiful talk. Now we will move to Yasaman. So Yasaman, she did her bachelor and master in physics and astronomy in her home country, in Iran, and then she moved to the US and started her PhD at the University of Connecticut, working on studying quasar accretion disks, and then she moved here in last April at Space Telescope as a postdoctoral researcher. And today she will talk about reverberation mapping, the inner environments of supermassive black holes. So please, Yasaman, the floor is yours.
Hey. Hi, everybody. I'm very glad to be here and delighted to give one of the first talks of the Discover Seminar series, and I'm thankful for the organizer of these talks. Today, I want to talk about the reverberation mapping of the inner environment of supermassive black holes. So by far, we know that almost all massive galaxies host a supermassive black hole at their center. Throughout this talk, I'm going to refer to these as quasars or AGNs. What I really mean here is this compact inner region of these galaxies where these targets have about 1 million to 1 billion times the mass of the sun. In the image, in this slide here, what you see on the left is a typical galaxy with an extent of about 10 kiloparsec. And compare that to the cartoon on the right, where we have a typical, image of a galaxy, image of an AGN extended to about 1 parsec. What I want to highlight here is the different orders of magnitude between their scales, and ultimately the radius of influence. So despite this difference in their size, what we see is that the galaxy and black hole are closely correlated. Now, despite decades of research, we still lack a coherent picture of what are the main drivers of the black hole growth. What is the connection between the galaxy and the host, and what is the role of the large-scale environment on fueling the black hole, and what is the impact of the black hole-driven outflows on the galaxy? And most of these studies between the black hole mass and the galaxy mass are limited by the large uncertainty in the mass measurement of the black hole itself. So now we do need to do a better job of understanding these measurements. But before I dig into that, I want to just highlight the different scales that we see in an AGN. Here I've listed the different components that we see in an AGN, starting with the black hole itself, identified by its event horizon. We have the accretion disk that is formed into a disk. The gas has formed into a disk, and then we have this so-called broadline region where we have this hot, dense gas rotating in lumps around the black hole. And then we have the dusty torus, which is like a donut shape engulfing the whole system. For local AGNs, it is possible to map the dynamical effects on the nearby stars, but we cannot really directly probe the structure of the matter as they fall into the black hole. Of course, there's exceptions here. So there's the famous case of the M87, where the Event Horizon team practically used Earth as a massive interferometer to resolve the shadow of the black hole. There's the case of the first quasar, 3C273, and also NGC 3783, where the gravity team were able to resolve the structure of this rapidly moving gas. And this was the first time this so-called broadline region was resolved. Now, if we do need to do a better job of measuring these black hole masses, understanding their inner structure, but we can do this for very limited targets, how are we going to do this? So here comes the reverberation mapping technique, also known as echo mapping technique. This is the only available tool to measure distances beyond 100 megaparsecs. And the basis of this is that the quasar environment is prone to dramatic short-term changes in the ionizing flux, which results in the variability of the quasar. And this variability gets echoed between different components, and different elements respond to this changing ionizing continuum, where the high energy repeats in lower energy after some time delay. So you can see in this movie here where we have the direct emission from the accretion disk in blue, but we also see a reprocessed light after some time delay re-emitting in red. So what we really care about is that time delay between the blue and red. So as one of the main components in an AGN, the broadline region responds to this the changes of the continuum flux, and these changes would propagate throughout the system. And then what we care about is this measuring this time delay. By converting that time delay to some scale, we can combine that with the virial theorem and also a velocity width measurement of one of the typical prominent emission lines in an AGN and get an estimate of the black hole mass. And this technique can be done for the target's low luminosity or high luminosity and doesn't depend on the angular resolution. So in principle, we can do this for any target, but in practice, this has been done for only 60 AGNs to redshift of less than 0.3 up until just a few years ago. And I'm going to talk about why this is the case in just a few slides. As one of the main byproducts of the reverberation mapping, radius luminosity is a famous relation between the radius of the broadline region in each beta and the continuum luminosity. This is a simple scaling relation between the broadline region and the continuum luminosity, which is very attractive to get an estimate of the black hole mass for a large sample of target. The point is you can use get a simple spectrum and get an estimate of the H beta emitting region, and from this scaling relation, you can get an estimate of the black hole mass. So it's very attractive when we want to go target when we want to look at many targets or also looking at high redshift samples. However, one needs to note that we have this relation that is calibrated for nearby local AGNs, and it's also only for H beta line. And in fact, if we add more targets to this, more high redshift, more diverse sample, what we see is that there seems to be an offset in this relation. And this may be because we have this sort of this local AGNs that are limited to a narrow range in the eigenvector 1 plane. This the principal component of a diversity of quasar. The figure on the right shows the previous local AGNs that are limited compared to the whole STScI quasar sample. So it looks like to do a better investigation of this radius luminosity relation, what we do need is to target a larger population of quasars, also look at higher redshift targets, and also instead of just looking at one emission line, we need to look at multiple emission lines. Now here comes the STSsRM, or the Sloan Digital Sky Survey Reverberation Mapping Project, where we target 850 quasars up until a redshift of 4.5 from spectroscopy and photometry, and this is a multi-year campaign started in 2014 and is planning to continue as a part of STScI, and really expands the current RM sample in the physical properties, in their redshift, in their luminosity, and the mass. And the highlight of this campaign is that it's producing the less biased survey in any way possible, because the only cut on the selection of this sample is only from the magnitude limit. So you're choosing this target from a very diverse background. So looking at the parameter space of the black hole mass measurements from reverberation mapping, this is how it looks like up until a few years ago, where we have the H beta masses in low redshift. We have maybe few targets in MG2, and a handful of carbon-4 measurements. And STSRM has been able to expand this by adding H beta measurements up to redshift of about 1, and adding about 60 targets from MG2, and also adding another 50 from carbon-4 measurements, covering up to redshift of about 3. Now, just a quick peek under the hood of how we do this calculation. This is a typical light curve that we deal with. What we look at is the continuum light curve, again, from the accretion disk, and in this particular case, I'm looking at an MG2 light curve as for the emission line. So what we do want to look at is what is the correlation between the two, and what is the lag measurement between these two light curves. And this is a result of a 4-year study, 2014 to 2017 light curve. Again, you can see gaps within the observations. And because of these gaps, we need to be very careful about what are the weights that we apply, what is our lag measurements. So we do need to apply weights to these measurements for our alias removal. And then in this particular case, we use 2 different methods to get an estimate of the lag. And in this case, it's a lag of 60 days. So again, back into this STSRM campaign, we are dealing with an industrial scale survey. So we need to be very careful about the statistical properties of these targets. We also need to be careful about what is actual physical reverberation rather than random noise. So in summary, what we look at is we are looking at lag measurements that have single well-detected peaks in their lag probability distribution, and we also want to look at lags that are significant from 0. And we also, on a general basis, we are looking at false positive rate of less than 10%. Now, the histogram on the bottom shows a sanity check of what we obtained from this industrial scale survey, where the gray is the insignificant measurement, and then the red is the significant measurement. And you can see that even without adding the selection criteria, we have a bias in positive lags, which actually shows us the physical reverberation actually happening. So before I showed you only 2-3 targets maybe that had MG2 measurements. Now with this study, we were able to add about 57 targets that expand this sort of radius luminosity regime. This radius luminosity is for the MG2 line, and before because there was just so few, there wasn't a radius luminosity relation before, so we're able to expand this by using these significant measurements that we had, and sort of doing a comparison of how it looks like compared to the H beta. What we see is that our best fit slope is kind of shallower than what we see from the H beta, but still consistent with the basic photoionization. So now just a quick summary of what I've discussed so far is that we do need reverberation mapping to measure physical sizes throughout light echoes. And the need for this multi-epoch monitoring campaign is because we have to we need to look at targets over time because of the different length of their lags. So we need to actually look at them over time, over multiple years. And the STSRM has been able to expand this and increasing the sample of existing reverberation-based masses by a factor of 150 more, and expand the parameter space in redshift, accretion rate, and also quasar emission line properties. Now, I would like to switch gears and talk about something slightly different, still within the realms of reverberation mapping. But now, instead of looking at the accretion disk and the broadline region, this time I'm looking at the different portions of the accretion disk itself. This is also called disk reverberation mapping or continuum reverberation mapping, where we're looking at the higher energy emission from the inner disk and also the reprocessed light from the outer edges or cooler emission from the outer edges of the disk. And this time we're looking at the correlations between these two light curves. And this is, throughout this, we can measure the accretion disk size and also measure disk stratification. How does the temperature profile changes as a function of these, the filters that we look at. And this technique only relies on photometry rather than the broadband reverberation mapping, which relies on photometry and spectroscopy. So again, going back to the STSRM sample, we started with a sample of 200 quasars, looking at their disk measurements. What we found is a sample of 95 quasars that have disk measurements from reverberation mapping. You can compare that to the previous campaign that are mostly limited to the local AGNs and sort of expanding the parameter space in the black hole mass and the redshift. Now, the idea of the measuring disk sizes was also to compare what we see in previous observations. So far, most of the reverberation-based campaign have been able to measure disk sizes that are maybe a factor of 3 or 4 times larger. But also, most of these measurements have been from local AGNs. And most of these measurements also find disks that are, as a function of their wavelength, scaled by a factor of lambda to the 4/3. So what we did is that we took our measurements and sort of compared with the basic Shakura-Sanyaev model and see what we got. So on average, what we found is that our disk measurements are broadly consistent with the Shakura-Sanyaev model. However, we see a lot of diversity in the disk. And you can see again the previous campaigns here at the gray data points and the model that we fit using our nonlinear regression to model the disk size. So we were able to map the temperature size scaling. So you can see at the top, we are measuring disk size. Then we also used the black hole mass and luminosity to measure disk size as a function of black hole mass and luminosity. And then we also found that we have an average of about 3-day excess dispersion, which might be related to either black hole spin or radiative efficiency of the black hole, or any unknown physics that we are not sort of contributing in our model. Another study that I led was to take a subsample of these accretion disk measurements and look at their UV optical disk sizes. The idea here is that let's see if their UV optical disk sizes are any different than the optical measurements. So again, we selected a sample of 8 quasars. We targeted these over 2 cycles of Hubble. And we found out that our measurements are, on average, again, consistent with the basic Shakura-Sanyaev model. This is one example of the quasar that we looked at. At the top, you can see the UV light curve, and then at the bottom, you can see the optical light curve from 4 different optical bands. One interesting thing that we found in this study was that we are seeing evidence of the diffuse emission from Balmer and iron-2 lines over discrete wavelength bands. So this is shown in the sort of open symbols at the top that are showing outlier lags in our measurements. This was seen in the low redshift target, but we haven't seen this in the high redshift realm. Another project that I've been involved in was the AGN Storm, or the AGN Space Telescope Optical Reverberation Mapping campaign. This campaign is a very rich data set targeting one of the local AGNs. And I'm showing you a cartoon version of what the campaign overview looks like, where we are looking at, instead of using reverberation mapping to measure mean time delay, this time we are looking at to measure velocity-dependent information, which tells us information about the kinematics, geometry, and the gas orbiting in. So this campaign has coordinated observations from XMM, NICER, SWIFT, and also ground-based photometry from 6 different sites. And the goal of this campaign is to understand what's happening in the virial orbit of these different UV emission lines. This campaign has been done before for only one more target in the UV. Ground-based observations have been able to successfully do velocity resolved measurements, but in the UV there has been only one more case before this. This work is in progress, but stay tuned for our results, maybe in a few months. Now, with this, I want to look into the future of what we have learned from the STSRM, and also look at what, given the observations that we have coming up from STSS5 and LSST, I want to highlight what is the possible work that I'm going to do. So STSS5 has a black hole mapper component, which is planning to continue all the way to 2025. It's practically STSS-RM multiplied by a factor of 4 and 5. We expect about 800 reverberation-based masses from a sample of 1,500 quasars. We also have LSST observations coming up in just a few years. And LSST is a wide, deep, fast survey which will cover the entire southern sky. It will rapidly monitor the entire sky and targets millions of quasars over a 10-year period. And in addition to that, LSST will have at least 4 deep drilling fields. These deep drilling fields are very important for continuum disk reverberation mapping, and will rapidly go over 6 different optical bands, and will provide immense data in photometry. Now, next, what would be interesting is to look at what would be the combination of the STSS5 and LSST would tell us. Now, on the figure on the left, what I'm showing here is the luminosity as a function of redshift of what we have so far learned from the STSS-RM. The field symbols show the STSS-RM, STSS-RM observations are the measured from reverberation-based masses, and then the open symbols are the STSS5 predictions. Now, going beyond redshift of 3, you see that there's no kind of predicted measurements. And it turns out going beyond redshift of 3 because of time dilation effect is going to be very difficult to measure the lags. Now, this is where LSST would become very important. LSST would cover a broad range of redshift. It's a very deep survey, so you can see the gray contours on the figure on the right. And LSST would be able to easily probe up to redshift of 5 and 6. So what would be very interesting is to combine what we have from the STSS-RM disk reverberation mapping, that is covering to redshift of about 1, and combine that with what we have from STSS-RM and what we learned from STSS-5 to obtain a black hole mass estimator. As we discussed a while ago, the black hole mass estimator that we so far have is based on the radius luminosity relation, which often turns out to overpredict the mass measurements. So it seems that we do need to, especially when we go to higher redshift, we do need to do a better job of measuring the black hole mass estimator. And if we can't easily do this with the reverberation mapping, we should do this with some other means of black hole mass estimator. So this is something that I'll be working on in the course of the next few years, but I just wanted to give you a highlight of what I'll be doing and what is the rich data set that we're looking at. And I'm going to close up with a summary. So far, STSS-RM has been successful in adding 150 black hole masses from multiple different emission lines, the H beta, MG2, carbon 4, and we have more emission lines coming up within the next year. This was the first survey result that went above redshift of 0.3, and the highlight of this was that it produced less biased survey in redshift and black hole mass, and it shows that the radius luminosity relation can be very different than what we actually see in the low redshift. And also, this was the first time that we actually were able to measure the radius luminosity relation in MG2. And in terms of the accretion disk measurements, we've been able to increase the sample by a factor of 10 using this STSS-RM survey. This was the first time this survey was done about a redshift of 0.1. And we did a very careful bias judgment because of the lag measurements that we did. But what we find is that on average, our disks are consistent, but with a lot of scatter. And then we also did an HSD accretion disk reverberation mapping, which gives us information about the inner edge, looking whether the UV optical disks are any different. And what we found is that the UV optical is pretty much the same as the optical measurements. Or it may be that our measurements are our sample of 8 quasars out of the 100 target that we measured, out of the 100 target that we selected, were biased to larger disk sizes. And for the first time, we were able to find evidence of a diffuse contamination in the UV optical disks. And with that, I'll be happy to take any questions.
Thank you very much, Yasaman, for the great talk, great results. You can stop sharing your screen. So let's see if there are questions in the chat, or if anybody wants to ask a question, you can raise your hand from the Blue Jeans app. John Debs has a question.
Hi, great talk, Yasaman. Thank you. You had mentioned that in your last slide that there's a lot of scatter in the disks, and that is caused by a diversity of disk sizes. Can you talk a little bit more about that? Like, do you think you're seeing different structures, or just that it's sort of measurement noise more?
I don't think it's measurement noise. It's mostly because what we think is that the Shakur-Sanyaev model is a simplistic approximation of the disk size, but it also is, and we know this is not right, but we also don't have a better solution for that. It's just what we think is that we do need to add corrections to this, whether it could be spin, whether it could be efficiency of the black hole. In the Shakur-Sanyaev model, we have mass to the 1/3 and accretion rate to the 1/3. And there's a lot of thing that is embedded in that accretion rate to the 1/3. There's a lot of conversion. There's volumetric conversion that we do, and that's the best we can do, because how do you interpret accretion rate in terms of physical observables? So I think are we measuring volumetric correction wrong? Are we doing the efficiency wrong? So all of those components are its own, realm of investigation.
Thanks.
Thank you. So I don't see other questions in the chat or any raised hand. So let's thank Yasaman again for her beautiful talk. And it was and I want to thank again both Yasaman and Cassi for being the first two speakers of our this new discovery postdoctoral series. And so thank you very much, and see you again in 2 weeks. We will have other two postdocs talking about their science here from Space Telescope and Johns Hopkins. So thank you very much, and see you next time.
Thank you.
Thank you.